For my project, I decided to focus on a school in South Africa and try to get them solar electricity. First, I started off by designing a problem. So the design problem for this project was a 400 square foot school/community center in South Africa has developed a need for electricity. Due to its remote location and funding, on-grid electrical is not an option. Because of this, the school has requested an off-grid electrical unit that can power lights, 6 laptop chargers, and a hot plate. The school site is open and does not have a lot of trees. This, along with the lack of a flowing water source and lack of constant wind, makes PV solar panels the best option. For this project, I have been asked to configure and design a small-scale PV solar panel system that can power a hot plate, lights, and an outlet to charge 6 laptops. The latitude of the building is about 33 degrees, which means that the angle of the solar panel should be close to 33 degrees for the optimal solar energy input. So some important problem aspects to be configured were solar wattage need, hours of sunlight for the prospective area, effective energy storage system, an efficient way to convert DC to AC electricity, types of wires to maximize efficiency, and the method of wiring lights, hot plate, and one of 2 outlets. For the next part, I decided to add in some history, impacts, and trends of photovoltaic solar panels. I'm not going to go through and read all of this for the sake of time, but some of the main topics that I hit on were beginning stages of solar panels in the 19th century, solar panel discoveries and economic incentives in the 20th century, and lastly, for history, the 21st century economic solar push. That pretty much encompasses the entirety of the history of solar panels. There was some stuff I wasn't able to add due to space in the paper, but for the most part, this was a pretty comprehensive summary of it. After that, I decided to go into different aspects of impacts of solar energy, starting with societal and cultural impacts. And the way I did this was I decided to compare this to other energy options, specifically coal and natural gas. After this, I decided to go with economic impacts/implications compared to other energy options. Here you can definitely see where I compared it to natural gas in different residential communities and cities. After that, I went into environmental impacts and then political impacts. After that, at the end, I started covering some trends, starting with current trends and then ending with future trends. And at the end are my list of references. After the research side of this was complete, I started working on possible solutions. And this can be seen in the design log tab of the website. So for my first possible solution, I decided to play around with the idea of 2,000 watt solar panels on the roof of the building with a 33-degree pitch facing south, which is the optimal pitch for collecting the solar rays. Wires will be run to a charge controller and battery pack, and then to a 220 inverter. Then they will be run into a house breaker box with 4 breakers with wires running from the box to the lights and 2 electrical outlets. The 20-watt system is optimal to use all the required appliances at the same time, and it would allow the school to cook for longer periods of time while charging the laptops. So here below we have a small little diagram. Here's an example of what would be the hot plate. Here are the solar panels with the right pitch, with wires running to the battery charge controller, the battery pack, then to the AC converter, then down to a house breaker box, and lastly out to the ground to make sure if lightning was to strike the building, it would not fry the entire system. Now on to solution number 2. The 15,000 watt solar panels would be placed outside on the ground with a 33-degree pitch, with wires ran underground to the school. Inside the school there would be a box with batteries, charge converter, and AC converter. The inverter would have 4 220 plugs on it so that it could be used as the outlets. The LED lights are wired straight from the solar panels on DC power. And this solution was optimal because even with the less wattage, it would really allow for a lower resistance and wattage loss due to the lack of connections and wire links. Here's a short little diagram about solution number 2. Here you can see the solar panel here. I drew it a little bit too close to the building, so there's a divider line in between the solar panel and the building saying that it would be about 20 feet away from the building, with the wires run underground just to make sure that nothing above ground would corrode the wires. Inside it would be run into a box. The box would have plugs on the inverter here, a battery pack, and the charge controller would also be inside this box. Then it would be run, and then wires directly from the solar panel would be run up to wire the LED lights at the top. Lastly, there's solution number 3. These are 1,000-watt solar panels. They're on the roof with the same degree pitch as the first solution and still facing south. The wires are ran from the solar panels to a charge converter and battery pack, then to a 220 inverter. The 2 outlets and the lights would be wired from the inverter. The 1,000-watt solution, while as it doesn't have the energy output that the other solutions have, it would be really cost effective. And even though it wouldn't have a very large output of electricity, a large battery pack would still kind of help offset that and allow the school to be successfully powered with these solar panels. Next, we would be looking at the implications of these solutions. So, first off, on this tab, I decided to lead off by saying all of the implications for all solutions, because a lot of the solutions are relatively similar. They just have some small things in them that make them very different in terms of PV solar design. So first would be direct implications for all solutions. The solar panels installed will be able to create enough electricity to power lights in the building, which will allow the teacher more time to teach students. Laptops would be charged by the solar panels in the classroom, which will save time and allow the students to be on their laptops for longer amounts of time. And lastly, the hot plate in the classroom would allow students to receive hot meals while they are in school. Some of the indirect implications for all the solutions, I decided to make 2 columns with this, positive and negative, just to kind of give the 2 different sides of what the indirect implications would be. First, the positives would be the hot plate could be used down the road as a means to give more people in the community access to warm meals. Second, the newly lighted space could serve as a meeting area for the community. And third, with the new electricity, more students would be able to join the school or be more interested in going to the school. Some negatives would be solar panels are expensive and could be stolen, leaving the school without power. The batteries could have an unexpectedly short life, causing them to need to be replaced, which would be a huge problem in an area such as South Africa, because they might not have access to batteries like this for long periods of time. And lastly, solar panels could be damaged in a storm and the school wouldn't have enough money to replace them. So for solution 1, the specific implications for solution 1, direct would be with 2,000 watts of solar input every hour, the school would be able to run appliances more often and for longer amounts of time. And the house breaker box would not allow electrical surges to destroy the system. Some indirect implications would be higher load on the system that could cause potential system burnout. It could sell power back to the grid later on. This would allow the school to kind of have a source of income. So, for example, if the school was able to sell enough electricity back to the grid, they could potentially make enough money to have Wi-Fi in the school to further help student learning. Third, the cost of extra wire to wire the electrical box and the breakers would be difficult to replace. It would be pretty difficult with the amount of wire used, because if it did short out, then the cost would be extremely high, and breakers are not easy to find. Lastly, higher strain on the batteries and charge controller would potentially cause quicker fail rates in the system. And this is something really important to consider, where they might not be able to have somebody be able to come out and fix that for long periods of time. For solution 2, some of the direct implications would be a 1500 watt system is enough energy to replenish the system most of the time. However, on cloudy days, the batteries would need to be used more often than on sunny days. The solar panels on the ground would lessen possible wind damage during storms and be easier to ground, naturally, because it's on the ground. Underground wires would help increase wire longevity because the added protection from the environment. LED lights are wired DC to help decrease the load on the AC inverter. AC inverter is used as the outlets needed for the laptops and hot plate, cutting down on wire resistance costs. This is important because with the less wire that's run, the less resistance you're going to have, and the more electricity you're going to be able to keep in the system. Indirect implications: the solar panels on the ground are easier to steal and can be damaged by people or animals walking by. Underground wires can be severed unknowingly, causing the system to fail. Another thing with having the wires underground is that if they are cut, they're going to be extremely hard to replace, because you'll have to pull up most of the wire because they're very difficult to splice. With everything plugged into the inverter, if something is plugged in wrong, it could short out the whole inverter, causing the system to fail. When everything's relying on one piece, if that one piece goes out, the entire system goes down, which would be a huge problem. If the batteries and inverter failed, the DC lights would continue to run properly, keeping the building lit, which would be really good, because then they would still be able to hold classes for longer periods of time. For solution 3, direct implications, the 1000 watt system would replenish the batteries at a slower rate, causing for higher energy draw from the batteries. This would overall cause the system to kind of last a lot longer than, let's say, a 2000 watt system would last with the same batteries. Second, 3 outlets wired from the inverter would allow for more devices to be plugged in and more places to charge a laptop. This would mean that, let's say the students were using their laptops in class, they would not be held to only be able to charge their laptops in one spot. They could plug it into a wall outlet that's closer to them. And lastly, like I said earlier, the 1000 watt system would put less strain on the charge controller and the AC converter, along with the battery pack. Indirect implications: a 1000 watt system won't be able to power any extra devices that are plugged in for very long. Too many days of low sunlight could cause the school to run out of power for a short time, and a power surge could knock out all the power, including lights. The problem with choosing solution 3 would be with the lower wattage system. If they had a week of rain, then the batteries would most likely be drained by the end of that week, causing the school to be without power for a bit. Next, we're going to move on to the troubleshooting aspect of this project. So, when I was troubleshooting, I came across 3 real issues that I had to kind of solve, and below I'm going to read here in a minute how I decided to go about solving each program or each problem. For wire sizing, after I decided the system size, I had to decide the best way to wire up the system. Even though I am not yet doing this full scale, the sizing still took a considerable amount of time to get right. Originally, I had decided to wire the system with 2 AWG grade wire for low resistance ratings. However, this type of wire would create a working solution. However, it would be overkill for the system because it's rated for almost twice the amperage I was using. So there would be less resistance, but it would also cost a lot more and just be completely unnecessary. After realizing this, I decided I'd redo my calculations using 6 AWG wire that was rated for the 65 amps that the solar panels would put out. This is a little more than the solar system required, but it also helps keep the wiring system cool and just kind of balance the load a little bit better on the system. And after the calculations, I realized that the loss of voltage in 6 gauge wire was low enough to run the system effectively, and really wasn't that much different than using the 2 AWG gauge wire. Second, I came across some issues with solar panel wattage. The solar panel sizing is arguably the most important aspect for small solar systems, because if you don't have enough wattage, then you won't be able to run what you need to run, and if you have too much, then it could burn out your system and cause problems later on and just be more expensive than what you really need. So when I first started out, I had picked out a 2000 watt system as my solution, but I quickly realized it was a mistake. When sizing the panels, I decided to go on a system size bigger than the total load of the system could draw. This was a problem because then I would never have any issue with powering the system, but there was no need for that much electricity with the battery pack I was using. So I decided to go with a smaller 1000 watt system. This system, with the help of the battery pack, could provide enough power to run the hot plate, lights, and laptops for about 21 hours straight before depleting the system. And lastly, I decided to go about how to decrease resistance. I experimented with several different types of delivering power through the school. At first, I was set on trying to get a house breaker box to distribute the power. However, after looking at potential losses through connections and extra wires, I decided it wouldn't be beneficial for this small of a system. When I realized this, I decided to go with an AC 220 inverter with 2 outlets wired in, which negated the extra energy loss through the longer wiring systems and connections. So basically, I cut out the connections through the box, through the breakers, and the wired outlets, which saved me a lot in the long run, a lot of energy in the long run. Next, we're going to talk about the final solution and the calculations that were made to kind of determine that solution. So for my final solution, I decided to go with a 1000 watt solar system with the panels placed at a 33-degree angle facing south on the roof to maximize efficiency. I decided to use 6 gauge wires to connect the solar panels to the battery controller and 1/0 wires to connect batteries to the charge controller and connect the batteries in parallel. The battery pack consists of 2 Optima Blue Top Deep Cycle Marine 12-volt batteries connected in parallel to create a maximum storage capacity of about 20,000 watts. These batteries will allow all electrical applications to run at the same time for about 21 hours. If the sun is charging, the panels, about 21 hours if the sun is charging the panels, or about 11 hours without sunlight. The batteries will be connected to the 1000 watt AC 220 inverter using 1/0 gauge wire, and the LED lights will be wired straight from the inverter using 14 gauge wire, which is used with American Housing Code. On the inverter, there will be 2 20 outlets, one for the charger, the laptop charger, and the other for the hot plate. The charge controller, battery pack, and inverter will all be secured in a wooden box placed in the corner of the building to allow for accessibility and shorter wire sizes. Specifically, the inverter will be mounted to the top of the box with a hole cut out, or 2 holes cut out, to expose only the 2 outlet ports. So here are some of the major parts. I'm not going to go through and read all of these, but down here are the feet that you would need for each set of wire in order to wire up the whole system, the type of amp, the power inverter, and the 1000 watt solar panels. So the calculations for the solution. For the PV solar panels. Solar panels will be placed at the regular degrees, south. So for the 1000 watt system, the way you would calculate that would be to decide how many hours of sun a day would be in your area. So for instance, here in South Africa, it'd be about 5.5 hours of sun a day. And so that would average out to you getting about 5,500 watts a day. It's a rather simple calculation. So, but taking into account the high solar radiation rates in South Africa, the average wattage and wattage per day would potentially be closer to 6,750 watts per day. There isn't a direct way to calculate that, so that's like the average that I got from this calculation output generator. So the amount of kilowatts produced annually by 4 250 watt panels with a square area of 2 square meters is what is calculated below. So you can kind of see on this chart It's a pretty simple spreadsheet which takes into account the losses through the inverter, through the temperature, the types of cable and electricity, the shading of your site, the losses in weak irradiation, losses due to dust and snow. That's set at 2% for the globe, but that varies differently based off site, and then other losses, which for this site didn't have any. And that came out to about 2,464 kilowatts an hour. The maximum power draw for this whole system, which is what I was calculating, was the hot plate, LED lights, and 6 laptop chargers. The hot plate, I would say, would draw about 1,200 watts per hour. The LED lights would draw about 27 watts. And the laptop chargers would be about 540 watts. And so below is the kind of estimated wattage. So that's the wattage per hour with hot plate on, and that's the wattage without the hot plate on. What's important to think about here is that in theory the school would only be cooking probably 2 meals a day, and that would only take about an hour at a time. So this total load here would only be used about 2 hours a day, whereas this load would be used basically the other 6 hours of the day that school would be in session. Below this we have the voltage loss. The wires between the solar panel to the charge converter, which we are using 6-gauge wires for, calculated out to be about 52 thousandths of a volt drop per foot. So that basically came out to a minute number that didn't really need to be, that didn't directly impact the solar system. The lights came out to about, they would draw about 1 amp of electricity, and so with that led me to determine it was 14 gauge wire, which would equal about 4.14 voltage loss over 40 feet. And then the outlets calculated out was about 0.02 voltage loss over about 10 feet for that gauge wire. And underneath there's a small note that says this loss rate doesn't directly impact the solar system. So, well, as I did really calculate the voltage loss, it didn't directly impact what I was doing, so they weren't really thrown into the solution. After that, we have the battery pack capability. So the 2 deep cell batteries, they can hold about 800 amps at 12 volts. And the way you would calculate that would be watts is equal to amps times voltage. And so that would show that they could hold a maximum of 10,000 volts individually, or about 20,000, a little over 20,000 together when connected in parallel. With a 1,000 watt per hour charge solar panel and a 1,767 watt maximum draw, the batteries could run at full charge for about 27 hours to about 21 hours, or or about 21 hours at 80%. So it would be 27 hours at full charge, and at 80% charge it would be closer to 21 hours. The reason I put in there the fact about the 80% charge is because most of the time your batteries aren't going to reach maximum charge. They're going to stay closer to about 80%. So this number is probably more or less what the school will be seeing. Without the solar panel input, the batteries would provide power for roughly about 11 hours. And here's the basic calculation. Just took how long the batteries could, how much electricity the batteries could hold together, or watts, and then you divided that by the maximum power draw to get about 11 hours. Lastly, I have the final solution log, which is just basically how you would go about the process if when this would be implemented. So first we have solar placement, as I've mentioned just a few times, the 33-degree angle facing south. And each set of panels will be bolted to the roof using metal support brackets. And here are 2 basic diagrams with the solar panel on top of the slightly inclined roof at about a 33-degree pitch, and then here's kind of like the front view on this side showing where the panels would be centered in on the house. After this, we have the solar bracket design. The brackets will have about 6 holes in them to bolt the panels to the roof. And over here on the right, there's an easy 10-degree adjustment for the different seasons. So the sun is different, the height of the sun is different for each season. So in the summer, it needs to be about 10 to 15 degrees different than in the winter. Next would be the wiring schematic of how the solar panels would be wired into the box. So once mounted on the roof at the proper pitch and direction, the solar panels will be connected in parallel, as you can see here. This would allow the wattage to increase while keeping the voltage and amperage the same. The last panel is wired through the roof and wall into a charge controller. So it would run right into the roof here, and it would run inside the roof over to the wall, and then run down the wall to the box that has the charge controller, batteries, and AC inverter. So here we have the basic wiring schematic for how the charge controller, batteries, and inverter would be connected. So the solar energy input would come in here, and then it would be exited, and then the charge controller would be hooked up directly to the batteries. The charge controller is really important because it makes sure your batteries don't get overcharged, and it makes sure the solar panels do not directly draw power from the battery system. After the charge controller is properly hooked up to the deep cycle battery, you would hook up the deep cycle batteries in parallel, connecting positives to positives and negatives to negatives. And then that in turn would be connected directly into your AC inverter to change the DC power from the batteries into usable AC 220 electricity. The reason the 220 is used is because in South Africa, where they were colonized mainly by Europe, their power is 220 instead of like America where we have 110. After this, we have a small the LED wiring schematic with 14 gauge wire. The wires would come out of the box here from the inverter and go up into the wall and over to the 3 lights that are mounted at equal distance on the roof. So I based out some estimates for the length of wire that would be needed to run to these LED lights. So it would be about roughly about 25 feet, which is allowing for a little bit of play. The actual estimate is a lot closer to 22 feet, but 25 would just allow to make sure you had enough wire by the time you got down there in case there were some issues with wiring the boxes. Lastly, I have a schematic here of how the wooden housing box and outlets would play out. The box would be about a 4x4 box that would be used to house the batteries, charge controller, and AC inverter. This would keep all the parts easily accessible and compact. Below is a schematic on how the AC inverter would be mounted to the box and the terminal, and with the outlet terminals for laptop charging and the hot plate. And that would be facing up to make sure that they could easily plug into the inverter. The metal support bracket that you can see run through here would be used to hold the box up to the top, and a lid would be placed over to ensure everything can't be touched by the kids inside the school, and it would be locked up here. So here are the hinges for the access door, and here to the right is a small picture of how the access door would look. Overall, that's a pretty brief summary of this project that was for the South African Solar School. I really hope to be able to implement this soon. I'm working with the professor now to kind of see what our possibilities are and how to get funding for it. So thank you.